this video is to take you through the presentation on NAND universal gate, or like NAND only design. This is Vasya. He often joins us for these videos, and he has been really stubborn today about sitting in my lap. So yeah, he's just been super stubborn about sitting in my lap. So I get up and I move, and he just comes back. My mom would call him Pesty. So he's here. He's a good cat though. All right, so let's do this. So the presentation topics, basic function of the NAND gate. We do want to review that and make sure we're really clear on what NAND gates do. And then go through how a NAND gate can be used to replace the AOI logic that we have already. So your AND, OR, and inverter gates. How can you take out an OR gate, and replace it with NAND gates that would do exactly the same thing. Then we'll go through the re-implementation process. So hopefully I'll do that example pretty well on the video. We'll see. And then going through the why would I ever want to do this? So why would you ever take your AOI logic and then re-implement it with only NAND gates? And then you can kind of tell on the bottom of this slide here, pretty much it boils down to money. So even though NAND logic might implement more gates, because those gates are all the same, you often will use fewer ICs. That should say fewer instead of less. That's gonna bother me. But you would use fewer of the actual chips in your circuit, and so that would end up saving money in the long run, especially if you were doing a lot of circuits. This is what your assignment at the end is going to be, just to give you an overview so you know where we're heading with this. So the block diagram below represents a voting booth monitoring system. So here we have our booth monitoring system here. For privacy reasons, a voting booth can only be used if the booth on either side is occupied. So booth A can only be used if booth B is not used. Booth B can only be used if A and C are both vacant, and so forth. The monitoring system has 4 inputs and 2 outputs. So that makes this a little bit different than the things that we've been doing before. So instead of 1 output, we now have 2. We're going to have 2 LEDs, and they have to do the right thing at the right time. Whenever a voting booth is occupied, the corresponding input booth A, B, C, D is at a 1. So what that means is if somebody comes in and they choose booth C, so I don't know how many of you have had a chance to vote yet. It kind of depends on when we have elections and when your birthday is, but no. Rethink that. That's a terrible idea. Okay. Right, he's gone for the moment. So when you go in, usually you have a choice of which booth you're going to go to. You kind of look around the room and see where you want to go. To my knowledge, there are no rules like this. So this would maybe be if you don't have privacy curtains or something. Most voting, like if you're going to vote in an election, there's a curtain that you can draw so people can't see what you're voting for. But let's assume in this case there isn't. So somebody comes in, they go to booth C. Booth C is going to output a 1. Okay, and so we're going to have like a 1 going in. So our input would be 0, 0, 1, 0. Now, if somebody else comes in while somebody's in booth C and they go to booth A, then the input would be 1, 0, 1, 0. If somebody comes in and goes to booth B, now we have 1, 1, 1, 0. Okay, the first output booth is a 1 whenever a voting booth is available. So if you're walking in and you want to know, is there a booth available? So if somebody is in A and C, there are no booths available. So that would not be on. So we're not going to have like a 1 there. But if somebody's just sitting in booth C or voting in booth C, then booth A is available. So you would have a 1. The second output, alarm, is whenever the privacy rule is violated. So you have someone in A, someone in C, somebody in B comes in, and we go to 1, 1, 1, 0, and the alarm goes off. Okay, and honestly, it doesn't matter. So we've talked about the don't care situations. There are don't care situations here. So let's say somebody is voting in booth D, okay? Well, there are booths available, okay? And then somebody comes in and they're like, I'm going to go vote in booth C. Now, if you've got somebody in C and somebody in D, technically A is still available, but it doesn't matter because the privacy rule was violated. And so the alarm is going to go off. And so that would be an instance where you don't care what the output for the booth is because the alarm is going to override what's happening in the booth. In this activity, gotta make my picture go away. My picture is terrible anyway. It's like weekend, it's a scrappy weekend. In this activity, you will implement NAND-only combinational logic circuits for the 2 outputs, booth and alarm. These NAND-only designs will be compared with the original AOI implementations in terms of efficiency and gate IC utilization. In a future activity, these NAND-only designs will be compared to the circuits implemented using only NOR gates. So we go through this whole concept with NANDs, and then we get to do it again with NOR. Okay, it's called universal gate design. So that is what you are going to be doing at the end of the activity, and hopefully by looking at it at the beginning of the activity will help you know what kinds of things you need to pay attention to. PLTW actually sets you up pretty well to be able to do that. So a NAND gate. So that's what it looks like. It's an AND gate with the little negation at the end, okay? And so essentially what it does is it's going to AND X and Y together. So you have like X, Y ANDed together. And then it's going to negate the output. Boom, put the whole bar right over it. So an AND gate only goes high when both inputs are high. So an AND gate would be 0, 0, 0, 1. A NAND gate is going to take that 0, 0, 0, 1 and negate it. That's what that little piece does. And so we end up with 1, 1, 1, 0. So that is your truth table for a NAND gate. Note that De Morgan's laws can be used to rewrite the output as a sum instead of a product. So break the line, change the sign, cutesy little rhyme there. So break the line, we end up with X bar and Y bar, and then change the sign from multiplication to adding. And you can also see that in the truth table, if either X or Y is low, or both, then the output would be high. It's when neither of them are low that the output is low. So that's what a NAND gate does. Make sure that you're really clear on what this gate actually does. So now we get into this. This is the explanation of how you can take your AOI logic and replace it with a NAND gate. So suppose you want an inverter, okay? So you want to take X and run it into an inverter, like so. But now we're saying, well, you can't use an inverter. So what can you do instead? Well, if you want to use a NAND gate as an inverter, what you do is instead of using a separate chip for an inverter, you can run X into both NAND inputs and it will negate it. So what it does here, and they're kind of explaining it right in here, is it's going to AND X, which we know from our Boolean algebra is just X, and then the negation is going to negate it. And so just like this would invert X to give us X bar, that running the X input into both inputs of the NAND gate will essentially invert your X. And that is your explanation of why you replace it like this. An AND gate. Okay, so you want to just AND them together. Essentially, you don't want the little negation, okay? So we would just like a regular garden variety AND. The problem is that we're being restricted to NAND. Okay, we're being restricted. And so our NAND gate is going to automatically invert the output for us. So essentially, this is my adding to the slide here. NAND them together, and now you've got the opposite output for what you want. You've got the negated output. So what you do to get it back to the original is negate it again. How do you negate stuff? you negate it with an inverter. So essentially NAND them and invert the output again to go back to an AND. So this NANDs it, and then this is like putting another little circle on the end right there, and you're going to go back to just AND. And they work you through the Boolean here. So this is going to be the negation of X and Y. And then we're going to run it through an inverter, which is going to negate them again. And the two negations are going to bring you back to just X and Y. So if you want an AND gate, you can do that with two NAND gates. Probably wondering, this doesn't seem like it's more efficient because I'm using two gates instead of using one. And that is true. So we will address that. Like, why is this? Why do people want to do this? Now, this one is the trickier one. Okay, which I actually wrote on the slide. This one is trickier. So suppose you have an OR gate. So what it might be worth looking at is the truth table for the OR gate. So the truth table for the OR gate goes high if one or the other or both are high. And so we want to be able to get this output here. So what they're going to actually drive for is the negation of each one, like if they're ANDed together. So here's what you do. That probably wasn't my clearest explanation ever, but you're going to invert both of the inputs. Okay, so you're going to have X and Y and then invert them, so you end up with X bar and Y bar right there. Okay, so you're going to invert them. Now you're going to NAND together the inverted X and Y. So that means you're going to be taking X bar, Y bar, ANDing them together, and then inverting that. Well, now do de Morgan's laws. Break the line, change the sign. We're going to be breaking that top line there. So we're going to break the line into two pieces and then change it to an OR. And now you can see we have X bar bar, double bar, Y bar bar. And that would just be X or Y, which is our OR gate. Kind of cool in its own nerdy kind of way. So you could take one OR gate and replace it with 3 NAND gates. Again, probably wondering, how is that better? just bear with me. Yeah. So where do we go from here? This, if I make my head disappear again, you will want these diagrams where you can find them quickly. So what you should do here is pause the video and copy that down. That goes back over the last few slides so that you know how to take an inverter, what you're going to replace it with your NAND gates, how to do your OR and how to do your AND. So pause the video here and copy that down. I'm actually going to copy it down. You know what? You don't have to pause the video. So AND ends up being a NAND through another NAND. And the OR is invert. And then NAND them together. And then my inverter is just, I did not do that right. There we go. Okay, good. That should be enough time for you to copy it down. Right, so here's the procedure here, and I should have thought better about putting that block of text right there, but it'll be fine in class. It's just if you're watching the video afterwards. So if I'm starting from a logic expression, you want to implement the design with AOI logic. So you're going to start with your regular AOI logic. That's going to be your starting point anyway. You're not going to go straight to your NAND. Like, please don't, because it's a recipe for getting something wrong. In the AOI implementation, identify and replace every AND, OR, and inverter with its NAND equivalent. That's what you should have just copied down. So everywhere in the circuit that you have an AND gate, you're going to replace it with 2 NANDs. Where it's an OR, you're going to replace it with 3 NANDs, and an inverter gets replaced with an AND gate. Then redraw the circuit. It might be a mess, okay? But step 4 is actually where it comes out kind of neat. So identify and eliminate any double inversions. For example, like back-to-back inverters, because there's no reason to negate something and then immediately negate it again, except with all of these like inverters that are going to pop up in this, because all of these replacements are going to involve an inverter somewhere. you are going to end up most likely with lots of back-to-back NAND gates, inverters. And so you can eliminate those. It's going to really reduce what you have in that circuit, and then redraw the final circuit. And what do I have underneath there? It says step 4 is essential because your circuit will be a bit of a mess. Fortunately, it often simplified well. So that should be simplifies. Okay, so this one, try to produce a solution before revealing the solution on the next slide. It's actually not in the next slide anymore because I have thrown in, oh, my factoring with an area model video just finished processing. Not that you care, but just finished processing on my iPad. So we're going to do this one, hopefully okay. I won't mess up the example too bad, so you can see how it works. So we have here A, B, and C. C runs through an inverter, so this is going to be replaced with the NAND version of an inverter. And then we have 2 AND gates, so these are going to be replaced with the NAND version of an AND gate. And then we have an OR gate, and that's going to be replaced with the NAND version of the OR gate. And then we'll go through and find what we can simplify in that. So on the next slide, I have a teeny tiny diagram there. Hopefully you can see it okay. It's super small on mine. And I am going to try to write with my finger on the screen. So, blech. All right, so we have A, B, and C already off to a smashing start. So I'm going to start with that C, that inverter right here. So I'm going to kind of do this in purple. All right, so that inverter right there is going to be replaced with a NAND gate. And so to do that in a NAND gate, we're going to split the input and run it through the NAND gate. So right there, that inverter just got replaced with a NAND gate. Now I'm going to look at my 2 AND gates here. Okay, so this is going to be the output from the inverter with B. So here we go. And that AND gate is going to be NANDed together. And then we're going to take the output from that and negate it again. And then we'll use red and we'll do this one. And this is going to be C and A. So right there and right there. And we're going to NAND those and then split the output and NAND the output. Okay, and now last but not least, let's use a blue color. Okay, that these 2 are going to go through an OR, and what I'm literally doing, you guys know, like, I got my huge to-do list, but I actually on that slide before copied this down so that I could look at it and say, okay, well, what does an OR gate need to do? Well, we're going to need to invert both, and then NAND them together. And that should work. So that's the same gate, but with a whole ton of NAND gates in it. But let's take a look at it. So step 4 in the process is to identify extraneous like gates, particularly inverters that are back to back. So you have an inverter right here, but it feeds into a NAND gate. So there's not a whole lot you can do. But right here, we have 2 inverters back to back. So we've got the output right here, and then we're going to invert it, and then we're immediately going to invert it again, which is totally unnecessary. Okay, like there's no reason to do that. And so this right here, if you can see where I'm highlighting it, ends up being exactly the same as this. So we can eliminate both of those. And then right down here, we have the same situation where we have an inverter back to back with another inverter. And so we can eliminate those. So I was going to do this on the next slide, but I'm going to forget what I wrote. So I'm not going to do it on the next slide. So I'm going to try to do it again here. So we're going to have A, B, and C. C is going to need to go through that first inverter. Sorry, I kind of messed that up. So that first inverter. And then, oops, oh, shoot. Okay. And then the output from that needs to feed into a NAND gate right there. And then A and C are going to feed into a NAND gate. And then these two outputs just need to be NANDed together. And so that ends up just being, what, 4 gates? Just 4? Yeah, just 4. And the advantage here is that they're all the same. So we actually, after the simplification process, if you look at the original one right here, was originally 4 gates, but they were 4 different gates, which means that, or I guess 3 different gates. So you would need 3 of the black IC chips in order to design that circuit. Well, our simplified NAND version also has 4 gates, but they're all the same, which means that they can all be located in one IC chip. Even if we had a lot of NAND gates and it spilled into 2 IC chips, we would still have fewer IC chips than we would with the original AOI circuit. So that's that, and that's a blank slide. Okay, and then this is their solution to it. So it's worth taking a look at, because just mostly because my handwriting is so terrible when I do that. But here's the inverter, which gets replaced with the NAND. Here are the 2 AND gates, and each of those gets replaced with the NAND back-to-back NAND. And then your OR, the OR is the one that's kind of like the messy replacement. But this unit here goes in place of the OR gate. And there it is with all of the NAND gates in place, which is the same circuit that I had, only way neater. And here they are identifying those back-to-back inverters. So you're inverting and then inverting again, and that is completely unnecessary. So we can get rid of those and come up with this much simpler circuit with only one kind of gate in it. And this is their proof of equivalence. So what they're doing is they are kind of running through the Boolean algebra. So if this is C, this is C bar, and then this would be B and C bar inverted. And then this would be A and C inverted, because that's what NAND gates do. And then we're going to NAND these together, which gives us one of those hideous expressions, which probably when we were doing De Morgan's law, and you're like, wait, where would we see this? These like bars all over the place. Now you know. And what they're doing there is they're using De Morgan's law. So break the line, change the sign, and getting rid of these double bars. And what you can see is it's the same logic expression as for the AOI. And here's where we get into the why would we ever do this question. So the original design here had 4 gates, but it had 3 different chips. So you had 1 inverter, 2 AND gates, and 1 OR gate. This is the number of gates per IC. So there are 6 inverters in 1 gate. And what that essentially means is that you've got 5 inverters on that circuit board that you're not using. You're not using those gates at all. And you can't avoid like that some of the time, like you can't avoid it, but 5 unused gates, that's a waste of money to put the whole chip on the board and have that many unused gates. For your AND and your OR, there are 4 gates per IC, but you're only using 2 ANDs and 1 OR, which means that you have 5 unused gates. So you have to use 3 ICs to cover all the different types of gates, and you have 10 unused gates. that are going to go onto your circuit board. With the NAND implementation, there are 4 per chip, and we were able to simplify this down to 4. So that means we only need 1 chip, and we don't have any unused gates sitting on our circuit board. And that does, and like, if it's 1 circuit, it's not a huge deal. But if you're designing something that you're going to manufacture like millions of it, that can add up to a lot of money. And so the reason why we have this universal implementation is to streamline the number of different gates and the number of chips that you need to use. So that concludes this lesson. So if you missed the class, or if you needed a review of what we covered in class, I hope that this helped, and you should be good to go to do the activity.